and welcome to the effects of pH on enzyme activity. If you have a look at this graph here, we've got pH increasing along this axis, and then we've got the rate of reaction here. We can see that this point here is the optimum pH for whatever enzyme this would be. And we can also see that by decreasing or increasing the pH outside of the optimum range decreases the rate of reaction. It's important to remember that the relationship between hydrogen ions and pH, so if you have more hydrogen ions, you're going to lower the pH. So as you can see here, as we're increasing the pH, we are increasing the rate of reaction. So there's more enzyme substrate complexes being formed up until a certain point. So we know that after this optimum temperature, if we're adding more hydrogen ions, we're going to have lower the pH. So more hydrogen ions are being added, we're lowering the pH, it'd be down here. We know that so the hydrogen ions because the hydrogen ions are positive, so this positive charge is attracted to the negative R groups, which are around the active site. So if we had our active site of our enzyme, here, so this is our active site, and we're going to have lots of minus charges here, and then we're going to have the positive charges of our hydrogen, and they're going to be attracted and they're going to cluster around the active site. And by doing that, they're going to block the substrate from binding. So this can't bind now because there's too many hydrogen ions blocking the active site. So when this happens, they can't bind and there's no enzyme substrate complex is formed, which explains why the rate of reaction stops and is denatured at that point. So the rate of reaction stops or at the high and the low points because these hydrogen ions in excess will interfere with the hydrogen bonds and ionic forces in the structure of the enzyme, like the proteins. So we've got our hydrogen bonds hold structures like alpha helixes in place in the protein. So that's going to be distorted. So if we have alpha helix, these excess hydrogen ions will interfere with the bonds, and it's going to change the shape, which will change the shape of the active site. Will change the shape because the secondary structure here has been changed by the excess hydrogen ions. So the active site changes shape, so that it is no longer complementary. So it's not complementary to the substrate. So these two are now no longer complementary, so they will not be able to bind. So it's denatured and there'll be no rate of reaction at that point. So we can see that small changes either side of the optimum pH slow the rate of reaction because the shape of the active site is disrupted in some way. However, if the normal optimum pH is restored, so if we get back to this point, the hydrogen bonds can reform and the active site, the shape of it, is restored. However, at extreme pHs, the enzyme active site may be permanently changed. And so it cannot catalyse reactions once it has been denatured. Thank you for watching. Oh, and one last thing, it's important to remember that all enzymes have different optimum pHs. So this enzyme has an optimum pH here. Another enzyme might have an optimum pH here or here. So if you see another graph looking like this, all it's displaying is that there are different optimum pHs for different enzymes. For example, working in the stomach, they want more acidic conditions, and elsewhere it might be something more alkaline that would work at its optimum. Thank you.